Hello, friends, welcome to Multiverse YouTube channel. It's a one stop solution for Gate ESE, SSC JE, and for AE JE exams, and for college going students who are preparing for semester exams. In the previous class, we discussed on state, thermodynamic equilibrium, as there are four thermodynamic equilibrium. I told you thermal equilibrium, mechanical equilibrium, phase equilibrium, and chemical equilibrium. And we discussed on process, and further we discussed non-quasi-static process and quasi-static process. In quasi, now moving further, as I told you that non-quasi-static process is a rapid process where the intensive properties are not uniform throughout the system, and quasi-static process is a infinitely slow process where the intensive properties are uniform throughout the system. And I showed you through the diagram where I took a piston cylinder arrangement. In the above the piston I placed a packet of sugar crystals, and I explained you. Okay, now moving further, as I told you yesterday, in non-quasi-static process the intensive properties are not uniform. In that piston cylinder arrangement, I took the pressure as 10 bar and the volume is 2 meter cube. When I am removing the sugar crystal packet, suddenly the piston moves upward rapidly. Okay, so now moving further, for doing the analysis, I am taking pressure and volume. Pressure on this axis, pressure in bar, and volume on this axis in meter cube. Okay, and I told you that this is the 10 bar pressure, and from 10 bar it is going to 2 bar and 2 meter cube volume, and here is 10 meter cube volume. In quasi-static, non-quasi-static process, what is happening? It is taking a rapid process. And I told you that when I am taking a container, the gas is filled here, and when I am removing the sugar crystal packet rapidly, the uh, piston moves here, and I did an analysis at some intermediate stage, and the uh, gas molecules are randomly distributed. Okay, so at the intermediate stage, I don't know what is the actual pressure is. So when I don't know the actual what is the actual pressure is, so I will represent the non-quasi-static process. Suppose this is the stage stage 1 before removing the sugar crystal packet. When it comes to state 2, I don't know how the pressure is, how much the pressure is. I don't know actual the pressure is. So I will represent this non-quasi-static process as dotted lines. Okay. In for quasi-static process, as I told you that when I am removing the sugar crystals, one by one, this piston moves very slowly, very infinitely slowly, so that this gas molecules will redistribute uniformly. After so many months, when you are taking all of the sugar crystals, the piston reaches here. And I did analysis where at this some intermediate stage, so that when I am doing the analysis at some intermediate stage, I can tell how much the pressure is, because the pressure is distributing uniformly when you are removing the sugar crystals one by one. Okay. So during quasi-static process, system passes through number of equilibrium states. How? See here. When I am removing one crystal, it comes here, and again removing I am one crystal, it comes here. When I am removing again, it happens like this. All these are equilibrium states. When I am removing the sugar crystals one by one. Okay, now as I know the pressure of this equilibrium states, so I can show it has a solid line. Okay, so what we understood is this is the non-quasi-static process, and this is the quasi-static process. Okay. As I told you that when I am removing the crystals grain by grain, this is grain by grain, all these are equilibrium states. When all these series of equilibrium states through which system passes is known as path of the process. This is when these all equilibrium states are combined, when these all equilibrium states combine through which a system passes is known as the path of the process. So I can write it as this is the path of process. Okay. Series of equilibrium states through which system passes is known as path of the process. And I told you that quasi-static process is represented by solid lines, whereas non-quasi-static process is represented by dashed lines. Okay, now moving further, a new topic we are going to introduce: internally reversible process. Here, internally reversible process means, suppose I am taking a piston cylinder arrangement and I am considering a gas as a system and this is this is the boundary of the gas. Okay. Internally reversible process means if there is no irreversibility, if there is no loss within the boundary, there within the boundary of the system is known as internally reversible process. Okay, for every intermediate process, properties are uniform throughout. When how we tell the properties are uniform throughout? Because the process is a quasi-static process, means the intensive properties are same throughout the system. There is no viscous losses. The viscous losses are zero. Okay, I can write it as if there is no irreversibility within the boundary of the system. As this is a closed system, I told you that every intermediate state of this process, the properties are uniform throughout. For a closed system, at every intermediate stage of an internally reversible process, all properties are uniform throughout. That is, closed system passes through series of equilibrium states. And I told you that there will be no viscous losses. The viscous losses are zero. So for closed system, any quasi static process neglecting frictional viscous losses is an internally reversible process. Here, no irreversibility means no loss within the boundary. Okay. Here, neglecting frictional viscous losses are 0. We have to neglect these viscous losses and we should assume it as a 0. Now moving further, externally reversible process. Suppose now I am taking a container which is filled with a gas no, it is filled with liquid and vapor. This is the liquid. This is a hectic concept of external reversible process. If you understand this concept, this will be a cakewalk for you for entropy chapter and available energy availability. Okay, this is liquid and this is vapor. Okay, this is vapor and this is liquid. When I am taking the condition of liquid and liquid to vapor, suppose I want to convert this large amount of liquid totally into vapor. So the what I will do is there will be a heat transfer from surrounding to the system. Suppose the surrounding temperature is 100 degree Celsius of source I am having, and this container temperature is 50 degrees centigrade. Suppose I am supplying heat to this container of 50 joules of energy. What happens further is the level of vapor increases and the level of temperature decreases. Guys, please understand carefully, this is a hectic concept. The level of vapor increases. What I am doing again is I want the same level of speed when I was having at this stage 1. Okay, so what I have to do is now I am converting it into vapor to liquid. What I am doing is, just observe, as I know that this temperature is 50 degrees centigrade and the source temperature is 100 degree centigrade. Again, to convert this vapor into liquid, I have to extract the heat to the surrounding, but it won't come, it is not going to happen automatically because the surrounding temperature is 100 degrees centigrade and the container temperature is 50 degrees centigrade. So to remove this heat, I have to connect a device called refrigerator. To bring back again to liquid, I am using a 50 joules of energy and I am connecting a device called refrigerator which consumes a work of 25 joules of energy. Refrigerator consumes energy, na? It runs on electricity, which consumes electricity. That work only is 25 joules. Totally, the work done will be the heat interaction will be 75 joules. So what happens further is I will get the same level of liquid when I had previously. This is the case of externally reversible irreversible process. Sorry. So what is happening in the surrounding is, if you observe, carefully, I will take here the process and heat interaction which is taking place in the surrounding work interaction what happening in the first process. I am changing liquid to vapor, and in the second process I am changing from liquid to vapor to liquid. What happens in the first process, as you observed, that from surrounding there is a heat interaction to the system is 50. Surrounding is losing 50 joules of energy and giving it to the system. I will take, when the surrounding is losing 50 joules of heat energy and there is no any work interaction, and in the second state the surrounding is gaining heat of 75 joules of heat, and there is a 25 joule of uh, work interaction the refrigerator is consuming. Here, what is the net effect? The heat interaction is positive plus 25 joules, and the work interaction is minus 25 joules. Here, it is a externally irreversible process, and there is a loss in the surrounding. How loss is taking place? For example, I I was traveling in a train. I felt thirsty, and I bought a water bottle of rail Neer, chilled water bottle, and I drank it. Again, what I did is I filled that water bottle, which is available in the train, and I asked the vendor, uh, uh, please take this water bottle and give my 20 rupees. Here, now you can understand the difference is here the heat interaction is a low grade energy, and the work interaction is a high grade energy. Work can be converted into heat, but the work cannot be converted, but the heat cannot be converted into work in a cyclic process. That is why all the heat engines, petrol engines, diesel engines, or dual engines will have the efficiency less than 100. Okay. Now again, I am taking a container of liquid and vapor, at an equilibrium state, Now again I am doing the same process. I am having a source of 100 degree Celsius and supplying heat of 50 kilojoules joules, and here the temperature is suppose 75 degree Celsius, and this the level of liquid decreases and the level of vapor increases. Again I want to convert this vapor into liquid. What I have to do is the same process what I have done before. Here the temperature of the vapor is 75 degrees Celsius and the surrounding temperature is 100 degree Celsius. Because due to temperature difference, the vapor which we have to convert it into liquid, it won't convert because there is a huge temperature difference. So again I have to connect a device. Okay, again I am extracting a heat of 50 joules I am connecting a device called refrigerator which is consuming a work of 10 joules. Totally the surrounding is gaining 60 joules of heat. What happens further is the vapor is converted into liquid what we needed. This is again a externally irreversible process. Okay, this is an externally irreversible process. On comparing these two, irreversibility is decreased now, but still it is an externally irreversible process only. This is also a externally irreversible process. Now again moving further, I am doing the same experiment. I am taking a container which is filled with a liquid and vapor. I want to convert this liquid into vapor at an equilibrium state. The source temperature is 100 degrees centigrade, and this liquid vapor temperature is, suppose, 95 degrees centigrade. Now I am supplying a heat transfer of 50 kilojoules, 50 joules of energy, heat energy. Again, it is going to convert, and the level of vapor increases. This is vapor and this is liquid. Again, I want to convert into vapor into liquid. Again, I am using the same, the refrigerator device, and I am extracting heat. The temperature of the is here 95 degree centigrade, and the source temperature is 100 degree centigrade. I am extracting heat at 50 joules, and I am connecting a device called refrigerator, which is consuming 3 joules of energy. Totally, it is. Sorry, guys. I did a blunder. I didn't explain the above process is what is happening in the surrounding. For the above process, I forgot to tell what is happening in the surrounding. Process is for surrounding which process is taking place, and there is heat interaction, there is work interaction taking place in the surrounding. For liquid to vapor, what is happening? There is a loss of 50 joules of heat energy and there is no work interaction. From vapor to liquid, there is a surrounding is gaining 60 joules of heat interaction and losing 10 joules of work interaction. This 10 joules of work interaction. Okay, so what is the net effect is plus 10 joules and minus 10 joules. There is on as I told you before, on comparing, irreversibility is decreased, but now still it is a externally irreversible process only. Now moving further, again I am performing the same experiment at equilibrium state. I am converting liquid into vapor, and this is the vapor liquid. Heat to this system of 50 joules of heat energy, and this is converting into vapor. Yes, again now I have to supply heat to the surrounding. I have to extract heat to the surrounding from this system. I'm extracting 50 joules of heat energy, and I am connecting a device which is consuming 3 joules of energy, and total heat interaction to the surrounding, which is heat gained by the surrounding, is 53 joules of energy, heat energy. Again this vapor is converted into liquid. This is the vapor at the beginning we gained it. Sorry guys, there is a small glitch. This is the liquid. This is the vapor. This vapor. The surrounding temperature is 100 and the system temperature is 95 degrees Celsius. I am extracting the heat of 50 joules from the surrounding, and again I am converting this vapor into liquid. The source temperature is 100 degrees Celsius. The system temperature is 95 degrees Celsius. I have to convert this vapor into liquid, and to convert this vapor into liquid I have to connect a device called refrigerator, which is consuming 3 joules of work interaction, and this is 50 joules of energy, total 53 joules of energy. Now what is happening in the surrounding is please pay attention guys. This is also a externally irreversible process. Again, by comparing these three, irreversibility is decreased, but there is still, it is a externally irreversible process only. What is happening in the surrounding for surrounding and converting liquid into vapor. What is the heat interaction? The surrounding is losing 50 joules of heat interaction and no work interaction is there. And in the second process, vapor is converted into liquid. Totally, surrounding is gaining 53 joules of heat interaction and there is a loss of work interaction of 3 joules. Here the net effect will be plus 3 joules and here the work interaction will be minus 3 joules. You can observe here is the irreversibility is decreasing slowly, but it is a externally irreversible process only. Now coming to final stage, again I am taking a container which is filled with liquid and vapor. At an equilibrium state, this is the vapor and this is the liquid. The surrounding temperature is 100 degrees Celsius and the system temperature is 99.99 degree Celsius. Now I want to convert this liquid into vapor. I am extracting 50 kilojoules of 50 joules of heat interaction from the surrounding and this liquid is converted into vapor. And this is the liquid which is remaining. Again I want to convert this vapor into liquid. Again I have to connect a device. This temperature is 99.99 degrees Celsius and the source temperature is 100 degrees Celsius. As I told you that it is not going to happen automatically, we have to connect a device called refrigerator which consumes energy called electricity. Here it is extracting a heat of 50 joules and we are connecting a device of refrigerator which is consuming 0.001 joule of energy and the total heat interaction to the surrounding is 50.001 joule. Okay, again here the liquid is vapor is converted into liquid. This is also a externally irreversible process. No, sorry guys, I am doing a blunder. What is happening to the surrounding is for the surrounding, what is happening here, the process is taking place and there is heat interaction, and this is the work interaction. We are converting liquid into vapor in the first stage. There is a heat interaction of minus 50 joules as surrounding is losing heat and there is no work interaction. And in the second stage, vapor is converted into liquid. The surrounding is gaining heat of 50.001 joule of energy and losing a work interaction of 0.001 joule of energy. Here the net effect will be plus 0.001 and the work interaction is minus 0.001. Guys, here you can observe is that it is nearly approximately to 0 and the work interaction is nearly approximately equal to 0. Here what I can conclude is that when you are supplying 50 joules of heat interaction from the surrounding in the liquid to vapor phase and the same work interaction is taking place, so it is a externally reversible process. Now on comparing all these four stages, the irreversibility decreased and finally we concluded to externally reversible process. What I am trying to tell is that heat transfer through finite temperature difference is an externally irreversible process. Heat transfer through negligible temperature difference here you can observe is that heat transfer through negligible temperature difference is an externally reversible process. In general, for calculation purpose, phase change process can be considered as internally reversible process. I am regaining my initial state from initial state again from liquid to vapor. Okay, so I can define externally reversible process as if there is no irreversibility outside the boundary of the system is known as externally reversible process. Heat transfer through finite temperature difference is an externally irreversible process. Heat transfer through negligible temperature difference is an externally reversible process. In general, for calculation purpose, phase change can be considered as internally reversible process. And finally, a process is said to be externally reversible process if there is no irreversibility outside the boundary of the system. As you can observe here, there is no irreversibility, means the net effect is approximately 0 only. By this I can conclude is that there is no irreversibility outside the boundary of the system. Okay guys, for today I will conclude this class here. Please guys, please like the session, share it, subscribe it, and for PDF please join Multiverse exam. Okay guys, thank you so much for joining the session.